Testing. Testing, testing, testing. Oh. Okay. Good morning, everyone. Bit louder than usual. What means testing? Okay. Okay. Are we ready to get started? Looks like it. All right. So today we're going to take a look at threads and how they be batteries. Any TAs here? No TAs? No, no one wants to admit the battery is dead. All right. I hope you can hear me. Gentlemen in the back, can you hear me? Okay, can forget about the mic then. So yeah, we are going to try to understand threats and basically threat behavior. So in order for us to do that, we'll have to look into your machine itself. Yep, because your threads are running on the machine. So we have to have some very basic understanding of the machine itself. Yeah, what your CPU is actually doing, so that we can understand why threads behave the way they do. Okay. Oh yeah, so I'm going to use Slido just to get some responses on the screen. Let's log on to Slido so that we can have some discussions. There we go. All right, you can join by scanning the QR code or by going to slido.com if it ever loads. There we go. Okay. Either scan the code or go to slido.com and enter the number there. All right. Just to test it out, you can answer the first question there. You're right. Should get 54 responses. Okay, so looks like most of you, only 6 so far. Everybody should be putting up either you're good at it or this one, yeah. Okay. Just want to see at least 50 responses, meaning everyone here is connected. Let me plug this in. Okay. So those who have never heard of it, do come and see me after class. Yeah. Most of you should be okay with it or good at it, or as half of you are saying, you were born to do this. Yeah. Okay. Just go ahead and make sure you can see the questions, and then we will prompt you with some questions as we move along. Yeah. All right. So today we want to introduce, to ensure that you are familiar with the two main terms, parallel versus concurrent. Yep. Very basic introduction to parallel programming, but we'll come back to parallel programming models in about 10 weeks time. Okay. So we'll go straight into it then. These are the terms you should be fully familiar with by the end of the hour, right? So what is a concurrent program? What you have been doing so far, you open your IDE, you have a main class, right? In the main method, you have some code, and then you run from the IDE, the code runs, right? So that is a sequential program, because you will write your program and it will execute your main method line by line. Even if your main method calls on another method from another class, right? It calls that method or that class does something, and then it returns something, and then it resumes, right? This is not concurrency, isn't it? Why? Your main method has paused, waiting for this to complete and then to pass back the value, right? So it is a sequential with a single thread of control. And do you remember last week I told you your main method, your normal sequential program that you have been doing is actually a thread, right? Okay. Therefore, but it only has one thread. Yeah, single thread of control. Whereas what we'll be doing for the next 10 weeks or so is where two or more threads are running virtually at the same time. Yeah? I say virtually because we will define that later. Yeah. So these two threads will be seemingly doing things at the same time, but actually they are both making progress at the same time. They could be doing completely different things, or they could be doing parts of the same job, whatever it is you program it to be. Yeah. So in order for us to, once we look at the output of these threads, first thing we have to understand is why is it able to do two things or more at the same time? So because we're talking about time, we have to look at computer time, right? How fast is your CPU running? How many instructions can it do per second? Oh, we're familiar with the CPU clock speed, isn't it? Can it do like 3 instructions per second? How many things is your CPU doing per second? Yeah. Assuming you have a i9 3.3 gigahertz. What does that mean? What does gigahertz mean? You all should know this, right? When you buy your laptop, you say, I want at least 4 gigahertz. The salesman will ask, why? I don't know. Sounds good. What does gigahertz mean? Yeah, am I talking to computer science students here? What is a hertz? You don't need to be an electrical engineer to know this. What is a hertz? Yes? Never heard of hertz before. Frequency, right? One clock cycle per second is 1 hertz. How many hertz are we talking about here? Your CPU? Nowadays they don't say anymore on the laptop, but you know your CPU speed, right? So we have to take that into account because your CPU is actually doing things in terms of nanoseconds, not even seconds, right? And we can't even fathom what a nanosecond is. It's just too fast. Okay? So bear in mind this ability of your CPU, because we can only perceive perhaps, not even a millisecond. We can perceive half a second, right? Like 500 milliseconds or so. So the reason why the threads seemingly are doing things at the same time is only because of our perception or our lack of ability to perceive nanosecond activities. Bear this in mind, then we'll understand how threads work. So when we talk about this concurrent and distributed software, this is very common architecture now. You have clients or machines communicating through a network, and all of these machines can be part of one system, right? Okay, very common. So when you have a single machine, then only one machine. What if I have 2 threads running here? There's only one memory, right? One RAM if you like. So there's shared memory interactions. These 2 threads have to share the same piece of memory, and of course, don't interrupt each other, right? And then when we're talking about multiple machines, then we have network interactions. So we have to manage data so that the 2 threads don't cancel out each other or override each other, isn't it? So that's what we are mainly going to be looking at. Okay. So why do we want to do concurrent programming? Of course, even when you wake up in the morning, you open your eyes, you are already multitasking, right? You see things, you hear things, you hear your breakfast being cooked downstairs. I don't know if you have some mates or your mom cooks your breakfast. All of this perception is happening. Oops, it took out his power there. One people when they come here. Okay. So now, obviously, we do concurrency to get performance gain, right? Because we multitask, we also need the machine to do so. And of course, we'll get more things coming out of the machine for a given slot of time, right? So that our applications can also be more responsive. And we'll talk about this in about 5-6 weeks. Some activities in your machine are more important than others, right? Some programs that are running in your machine have higher priority than others, correct? We can also manage that within your program. You might be running 5 threads, but thread 1 and 2, should be given more priority by the machine. So we'll be learning how to do that as well. And yeah, when we need to handle multiple activities and multiple events, and this is best done by having different threads taking care of different events. Okay. This is the promise of concurrency. So if I have one processor, yeah, one processor, come. There's plenty of seats on this side. Watch out for the trap. Okay. So question, if I have one processor and I give it a job and it takes 10 minutes for that processor to finish the job, right? What if I had two processors? Will it then take only 5 minutes to get the job done? Maybe, number one, if the two processors are equal. But will it take exactly 5 minutes? If it takes exactly 10 minutes, 10.00, 10,000, let's say it takes 10 seconds, so 10,000 milliseconds. If I have two processors, will it take exactly 5,000 milliseconds? Okay, so not necessarily there. That's the first question. So, oops. If also if we have multiple threads, some processors can take over if some of the other processors become busy. Yeah, we can distribute the work to different processors in different locations. Yeah, make space. Looks like all the seats are filling up. And I mentioned this just now, yeah? We multitask all the time. Okay? Our brain perceives so much concurrent, not actually concurrent, parallel inputs at the same time, correct? And we want to expect the same from our machines, yeah? So let's go back to question 1 and see if we can get some input here. Okay, before we go into the topic, why don't you answer this question first? We're gonna get into this very shortly. All right. It's a broad question, but let's just get some initial thoughts before we discuss it further. Because this module is called concurrent programming, it must be better, right? Otherwise, I'll teach you parallel programming. Okay. All right, so it looks like concurrency is more favored at this point in time. Watch out for the wires. Okay, so concurrency is the big winner here. We'll bear that in mind. Oops. And let's take a look at the next one then. You said it's better. So obviously then if someone is better than the other, then it can't be the same, right? Okay, looks like everybody already knows the answer to this, which is good. So they are obviously not the same thing. Although, when we talk about concurrency and parallelism in terms of the program, right? This should actually not be distinguishable by the user, correct? But you guys and girls, the programmers, you know that these are two very different things. Eh? Not very different, but there is a distinct difference. That's what we want to discuss. Yeah. Okay, coming back to my question one just now. Now, what does, we haven't defined parallelism yet, but let's answer this question first. So the idea is, if I'm going to do something in parallel, I'll need two people to do it, right? To do something at the same time. If I'm going to do a parallel program, I'll need at least two machines. They will both be running, doing something at the same time. So that's what the question is. If I get as much hardware as I like, we have about 60 laptops in here right now. Can I get 60 times speed up? Most of you say not really. Some of you are torn. And some are quite sure that is the case. Okay. Now, all of these answers can be correct, but not all programs can be split into 60. Agree? Yeah? You have to look at the nature of what you're doing. Yes, I have 60 laptops, but that does not mean I can distribute the work equally to 60, isn't it? So that's what we want to take note of, yeah? All right, let's come back to this. So this is how sequential programs look like, which you are familiar with. Your program will run line by line, correct? One line after the other, one task after the other. So this is how concurrent programs look like. Yeah? Multiple things are happening at the same time. And sometimes these individual tasks intersect or have to interact with each other. That is where we have to learn this, what we're going to be doing in this course. Okay. If I run two threads, and these threads do not interact or interfere with each other at all, they're completely independent. It's nothing for us to worry about, right? It's just like running two sequential programs, right? You start your IDE, you run program A, then you open your other class, you run program B. They're both running as two sequential threads, which don't concern each other, right? But we are talking about these types of programs where there are interactions, okay? Come back to that. So you all agree it's not the same meaning, right? So this is the definition you need to be able to define in your exam later. I can ask you a simple question, yeah? Not as simple as the one you answered just now. Are they the same, true or false? That's easy. Why is it not the same? How is concurrency and parallelism different? You need to be able to give me a nice, good answer in the exam. Okay? Here are some points for you to remember. So concurrency. Yes, two tasks are making progress. But look, at the same time frame, not exactly at the same time. Okay? So there, not necessarily at the same time. Why? What's actually happening? Why does it appear that they are running at the same time? It's because of time slicing. If you know what time slicing is? Yes? Time slicing? Heard of it before? Yes? Never. Okay. So time slicing is something you will need to know, obviously, for this module. I'll come back to time slicing in the next few slides. Even if I have one processor in my machine, can I run multiple threads? Only one processor. Can I run multiple threads? 10 threads. Yes, I can. Yeah. Why? Because of the CPU's ability to do time slicing. Okay. So now this is important. The concurrency concept is more general than parallelism. I mentioned last week. Concurrency is the broader concept. Parallelism is a subset of concurrency. Very important to remember why. That's why we are going to learn concurrency first. Everything I need to do in parallelism is a subset of the techniques in concurrency. Okay? And now what is parallelism then? At least two tasks are executing literally at the same time. What does that mean? I need at least two machines. Both are working at the same time. Whereas parallelism, it looks something like this. Sorry, concurrency. Oops, where's my, too far away. Really far away. Okay. I'll jump to this first. Okay. So this diagram basically summarizes the difference between the two. And I think it should make sense immediately, right? So concurrent. Yes, both lines of coffee drinkers, they are both making progress, correct? But each line takes turn using the coffee machine. So we can't, it's not going to run like this line will all have to get the drinks first. No, this guy will get the drink followed by this guy, followed by this girl. So both are making progress, but is it exactly at the same time? So we understand that that is what concurrency is, yeah? Whereas parallel, the two separate queues, there's two coffee machines. Now this line is making progress literally at the same time, correct? Okay. So a simple question in the exam. Don't draw this diagram. Explain it to me in a nice paragraph. The differences between the two concepts. Easy, right? Okay. Come back to this. So here, reading the file from the disk, the first line there, takes 5 seconds. So I have file A, takes 5 seconds to read it, 2 seconds to process it. So processing takes place at the CPU. Okay. Reading takes place in the hard disk. And then another 5 seconds to read file B and 2 seconds to process file B. So we do this sequentially. It will take 14 seconds if you total up the numbers, right? But can it be faster? Can we make it less than 14 seconds? Yeah, because two different hardware is involved, correct? So what we should do or what happens in your PC is 5 seconds to read file A. Now, whatever I've read from file A, it goes to the CPU, right? Why should I wait for this to finish? I'm going to immediately read file B. Correct? So that activity can happen at the same time, and we save off 2 seconds. Yeah? What's the big deal? 2 seconds. Well, 2 seconds in computing time is a big deal. Yeah. Okay. Even you press your app on your phone, right? 2 seconds. I've lost my patience. I uninstall. Correct. The thing hasn't loaded yet. It hasn't. The logo hasn't come out. This uninstall. In nowadays, very short fuse. Yeah. Okay. So here's more diagrams to help us understand better. Here is what concurrency looks like. Task 1 has 3 steps to do. Task 2 has 3 steps to do. They are going to take turns using the coffee machine like you saw just now. Okay. And then parallelism. Task 1, same 3 steps. Task 2 has the same 3 steps, except now that they are running on different machines. Both 1, 2, and 3 can run at exactly the same time. Okay. So anybody wants to revisit their question just now? Which one is better? Based on this diagram, is concurrency better? Based on this diagram, I think everybody will agree. No, yeah? Parallelism is faster. But my question just now was very broad, right? Which one is better broadly? I will agree with all of you just now. Concurrency is more widespread, more preferred. Why? Why? Based on this, how can it be that concurrency is more preferred? Very good. Look. Yeah, I only need one machine here, $100,000 server, right? Here I need $200,000 because I need two servers. Most companies will say, that's not what most companies will say. Most companies will say, anything that costs me more money, let it take another 5 seconds. I'll live with that, yeah? Anything that saves money is better, okay? At the end of the day, money talks, yep? So, concurrency versus parallelism, I asked you the question just now already. So, the answer to this question is, the absolute answer is, it depends, correct? Depends on what you need to do. Some companies, they have the budget and they have the need, they will do parallelism, yeah? By the way, parallelism now is done not by buying a new server, but just by subscribing to the cloud for more virtual servers, isn't it? The server farm already has 100 servers. When the company needs that speed, they will buy another virtual server so that the parallelism is there, yeah? So you know, Shopee, 3/3 sale coming up, right? At midnight. How is it that Shopee, but you will notice also at midnight on 3/3, what happens? You open Shopee. It's a bit shaky, right? It's a bit unstable also. What's happening? Normal load is 10,000 concurrent users, which is what one server can handle. 3/3 midnight, everything is 90% off. The load comes up to 100,000 concurrent users. This is normal. So what do they have to do? Buy one more server? For the 1 or 2 hours at midnight, they will have to pay their cloud provider for 9 additional virtual servers. Yeah. So if your company is serious about, user satisfaction and experience, you will actually subscribe to the 9 virtual servers so that you have parallelism to handle the load. Unfortunately, that's not cheap. Again, parallelism is all about cost, yeah? So most companies, I think you will also notice AirAsia sale or whatever. It just crashes, right? You just see a blank white screen, right? They'll say you'll just have to live with that. We don't want to we don't want to spend too much money, yeah? All right. So why are we here? Yes. If cost is high, if your cost is not an issue, yeah? Of course, then parallel will be not necessarily the default choice. Why? Not all of our tasks can run in parallel. Yeah, not all programs can be configured to run in parallel. Yeah, that's what we're coming up to. So here, why do we need to know about concurrent programming? Concurrency is actually, it's actually widely used, yeah, but error prone. This error prone part, we will witness it ourselves as we go through the labs later, yeah. The classical example is this machine, Tarak 25 from the 1980s. It's a radiation machine. It's a huge machine, looks like an MRI scanner. And every component of the machine is controlled by different threads. Okay? So all these different threads need to do their task and at some points coordinate with each other, yeah? So a laser thread, the power thread needs to control the amount of power to the laser, the radiation laser, right? Another thread needs to control the filters. Different threads control different filters. Combination of the power and the filters will shoot out just the right amount of radiation to treat this cancer or whatever it may be, yeah? So what happens if there's an error? This thread didn't know I'm supposed to put this filter. This thread said, let's put 100% power. What do you think is going to happen? That's exactly what happened, yeah? They're supposed to put a nice filtered dose of radiation. They gave out a full blast laser, it's like a laser shoot and ended up killing some people, yeah? We'll look at the video shortly. And yes, our Mars rover also. You know the Mars rover now on Mars? What's his name? Curiosity. Oh, there's another one, I can't remember. Every component of Mars rover is controlled by different threads. Okay? And these parts have to coordinate with each other, isn't it? The scoop, the arm, to drop the sample, to move the wheels, all different threads. And when these threads have problems, we have to reset Mars rover, just like our laptop and our phone as well, isn't it? Sometimes you have to restart it, correct? Why? Thousands of threads are running in your phone and your laptop. Sometimes it just gets a bit messy. A restart gives us a fresh start. Yeah. Here's the Tarak 25 machine. If you don't like to see burnt skin, I'll tell you when to close your eyes. Yeah. Oops. The video is a bit iffy here. Oh, I moved the folder. Let me show you the video here. So that's how the machine looks like. That's where the patient will lie. All right, take note of the term interlock there. We'll come back to it later. So there is a thread controlling the filter arm, another thread controlling the power, supposed to be X-ray mode. But then if they didn't coordinate properly with each other, instead of an X-ray, it became a lightning blast, yeah? All right. Take note of this term, very important term. It might come out in the exam, most likely, yeah? Race condition, we'll look at that because the main thing we need to avoid in this module is a race condition, okay? Just take note of that term first, we'll come to it. Now, these race condition bugs, yeah, are very difficult to detect. Okay. So after the treatment, they actually had radiation poisoning, and some of them had burns on their skins. And you can shut your eye now if you don't like to see the burn. Yeah. Okay. Don't open your eyes yet. Okay. Now, you guys and girls sitting in your desk doing programming, would you ever think that your boss will call you and blame you for burning someone's skin? Yeah. So don't think just because I'm behind this desk, I can't harm anyone. Your programs are going to be running in machines like this. And if you do not detect or you do not produce a error-free concurrent program in this case, then yeah, you are responsible for the burns, not the doctor, not the manufacturer of the machine, but the programmer. Okay? So, I'm not scaring you from becoming a programmer, but I'm saying that's why we are taking this course. All right? Now, bear in mind, 1980s, they were not fully aware of how threats behave in the machine. Okay? We are now fully aware, which is what I'm here to teach you, so that you are familiar with what happens in the machine, such that you can avoid the main problem just now, a race condition. Okay? So yeah, you can open your eyes now, whoever was sleeping or closing their eyes. Okay. So I asked you this question just now already. I jumped the gun just now. Now, the question just now, which one is better? Depends on your task. But remember I said, not all tasks actually can be parallel. And in order for us to do that thing in parallel, I can't just write one program and say I want two machines to do this. Which machine is going to do what? That's what you have to determine. That is what we call parallel overhead. Yeah, parallel sounds good. 10 machines all doing the same task at the same time. I should be able to do it 10 times faster, right? Not quite, isn't it? If you took 10 days, okay? 10 days to do some work. Okay, let's say programming lah, not hammering. 10 days to write a program fully to completion. But now I said, no, you don't have 10 days. I need it by tomorrow. Can you now grab 9 of your best friends, 10 people, and finish it by tomorrow? No, right? Why? Just sitting in a meeting determining what you and you and you are going to do, half the day is gone. Agree? That coordination. Same thing here, yeah? The synchronization there. What are you going to do out of the, 10-day task? And how is it all going to be combined together in 24 hours? Not likely, correct? So exactly the same thing here, yeah? At the end of the day, we want to multitask, and that's where threads shine, yeah? So multitasking is, we all know what it is. We all do it all the time, yeah? Sure, some of you are multitasking right now. Fully focusing on my lecture and fully focusing on something else also, right? So how is the machine able to do multitask? This is what we need to understand, yeah? So when some of you already have seen thread outputs yesterday, we have to understand how is it that the output looks or behaves as such. Now your OS, Windows, iOS, whatever it may be, it's able to multitask, right? How many tabs do you have open right now in your machine. If you do alternate tab, pop, 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 a lot of things are there, right? How is it able to just pop to different things there at any time? Because of the OS being able to share this CPU core among all the processes that you have inside. Yeah. So how is it able to do this? Remember time slicing just now? This is why we have concurrent programming to begin with. Okay. So that's your CPU. You have three processes in your CPU, P1, P2, P3. They all need to run concurrently. What does the CPU do? I'll run P1 for a certain time. We call this time quantum, time slice. Okay. So what's happening? We have time here. We're going to slice the time among the three processes. P1 will be given a certain time slice or quantum, and then the CPU will pause it. Now it will run the first few tasks of P2 and pause it. Run P3 and pause it. Go back to P1, see? So how is it able to do this? And yet we don't realize and we just see P1, P2, P3 running at the same time. How is that possible? Remember computer time just now? What is the time unit we're looking at? Is it seconds? The time here, computer time. Nanoseconds, right? Can you perceive 3 nanoseconds? You will not even know, yeah? P1, P2, P3 here will finish in about 10 nanoseconds, which you can't even perceive. That is what concurrent programming is doing right now in your machine. Okay? So the ability of the CPU to time slice is the key to concurrent programming, which we will be doing, yeah? So that's why we can have multiple applications running in the OS. Now, your CPU core, your laptop, how many CPUs does it have? Do you know? When you buy your laptop, did you ask the salesman? I want 8 core. No, nobody asked. Of course you asked, right? So a machine with 2 CPU cores, the OS will actually assign certain processors to certain cores. Which the more cores, the better, right? Typically, yeah. So that's how your multi-core machine. By the way, your phone also has multi-core, right? When you buy the phone spec, it tells you what? Quad core, at least, right? Nowadays, you need a quad core machine just to be at par with your friends, correct? Don't really care why how many cores it needs, but the more cores, the more multitasking your phone will be able to do. Yeah. Okay. Yeah. Let's take a short break at this point. I already put the question mark there. 5 minutes or 10 minutes? 30, then we go straight for lunch then. Okay, let's just come back in 10 minutes. All right. We'll resume at 11:45. 12 minutes lah. Everybody can freshen up. Yeah.
And Wagi, they was
You should have told me earlier.
they all just told me and I was because I didn't see my phone.
I forgot. Okay, tell them.
Okay.
Okay. Shall we continue? All right. Are we ready to continue? Yes, no? All freshened up? Some are not back yet. All right, let's continue. So, quick recap. If anybody was listening, please answer the question you see in Slido. So we're talking about the cores in your laptop or in your machine. Yeah. I don't think anybody has a 2-core anymore. At least quad. Mostly octa-core now, right? Or deca-core. Okay, so we get some sort of speed up, but if you remember from the diagram just now, so speed up and responsiveness are actually two different things. Yep. Here, if you understand what this diagram is trying to say, will your app, if you have a octa-core, what is octa-core? 8 cores phone. Will your app run 8 times faster? That's what speed up means, right? So that's not the case. Why? This diagram is trying to say that your single app, I don't know, one of your apps in your phone, that app will be assigned to a particular core. That app, most likely, I'm saying, some apps do, will not be run on all 8 cores. Why? Not all apps are designed, oh, you have 8 cores, I'm going to use all 8 of your cores and run 8 times faster. That's not what happens, right? That 8 core is there because you can now run multiple apps concurrent at the same time. So you know, you in your background, you'll be running this app. Then from this app, you go to this app to do some transaction, come back to this app, open another app. That's what the cores are for your multitasking, okay? So yes, again, not all apps are designed to run in parallel. It's not easy to be able to distribute a task across different cores, okay? So basically, the answer to this should be mostly no, unless you have a very specialized parallel programming app designed from the get-go to run in parallel based on the number of cores, then that's a different issue, okay? But generally, that's not the case. All right. Oops. So most programs are concurrent if they have independent processing steps that you can actually execute in parallel. Yeah. Or they can proceed in parallel by the program design. So this is called implicit concurrency. Explicit concurrency is you literally design the program from the get-go to run, to run concurrently, which is what we are going to be doing within the next few weeks. Okay. We are going to do explicit concurrency because we are going to control every step and all the synchronization of the activities we will be fully in control of. Yeah. So later, by the way, what we are going to be learning is concurrent programming. The same ways we synchronize the activities of 2 threads, 2 or more threads. The exact same approach is going to be used when we extend that to parallel programming, which means multiple machines, multiple computers, right? So a concurrent program is where what we'll be doing. We will define every action that can be performed at the same time, or some actions, although the thread is running, it should wait for an action for this thread to finish before it commences. All of the sequence of activities, you, the concurrent programmer, have to be in full control. The same thing with parallel programming. Yeah. If the task running on this machine starts when it's not supposed to start, it's supposed to wait for this machine starts to finish, disaster, right? If we don't coordinate the sequence of activities. Yeah. So there, a parallel program, very important here. A parallel program is a concurrent program, but designed to run on parallel hardware. Okay. So we first need to learn how to do concurrent programming before we even can think of doing parallel programming. Okay. And a distributed program. We hear about distributed computing or grid computing, right? It starts with concurrent programming. We can then do parallel programming, then that task can be distributed on the grid of multiple computers, okay, over the network. Right. So what we are going to be doing is the broader term to describe any program either doing actual parallel or potential parallel behavior. Okay. So parallel and distributed programs are all subclasses of concurrent program. So we are going to learn the basic core concepts, which will then be extendable to parallel and extendable further to grid or distributed computing, which is quite common. Yeah. When you have a server farm at your disposal, wow, the potential for the parallel tasks is tremendous, right? So that's, but the basic course will be actually within the concurrent programming spectrum. Yeah. Okay, so we are going to be using Java. Is Java the only programming language we can use for concurrent programming? No, yeah, by no, every programming language has a concurrent programming library or facility. We're using Java because it's the more common and widely available. We are going to be using one of the APIs called Java Util Concurrent. The library, yeah, we're going to import and we're going to use some of those. But before we use the library, we're going to learn the core concepts first, what the libraries are using. Because when you use a library, you don't really know what's happening inside, right? You just you just import and you use, right? But you don't know what's going on inside. We will spend the next few weeks learning what goes on inside first. Then I'll show you some of the libraries you can use, okay? So yeah, we're just going to be using Java. Every lab is, some labs are toy problems, which are like the applets that we're going to go through, yeah? Now, so concurrent programming, clearly there's some advantages, but there are some challenges, yeah? I wouldn't say disadvantages. They are harder to get right, yeah? But it's a myth, yeah? We need at least an order of magnitude in speed up for the concurrent programming to be worth the effort. It is going to be more effort than normal, as you will see as we go along. And the problems are very hard to detect. I don't know if any of you have a car, but from the early 2000s or late 90s. It's electronic, but the electronics from that era is very buggy. Sometimes, a lot of times, the warning light will come out on the dashboard. Yeah, it's beyond your time. You guys were not born yet. My time, yeah, when those cars first came out. What happens is concurrent programming. Yeah, the cars from the late 90s, they use an ECU in the car, right? Electronic control unit. The car is basically there's a computer controlling most of the sensors. Every sensor, every speedometer, everything is a thread that the ECU is actually keeping track of. So just like your laptop and your phone, sometimes the car becomes, yeah, too many threads going on, some clashing, some bugs, then the car will pop out a warning light on the dashboard saying something's wrong. It detected something wrong. And these types of problems, you might see it there. Okay, you drive back home, you turn off the engine. What happens? It's like a reset, right? The next morning you start, the light is not there anymore. Yeah, you drive to work, the light comes out. Then you go to the mechanic and try to recreate the light never comes when you're in the mechanic, right? These are the types of problems, exactly what we're talking about. Very hard to recreate a concurrent programming bug. And we will witness that as we go along the next few weeks lab, yeah? Now, again, one more thing I mentioned already. Some problems are inherently sequential. I have a 10,000 line of code algorithm. It has to run in sequence. I can't split that into 10 threads. There's nothing I can do. It's sequential by nature. Some problems are just like that, isn't it? Okay. And these are the specific issues that we are going to be addressing. When threads need to communicate with each other, when they need to synchronize their actions, and when certain parts of the threads cannot be time sliced. Yeah, certain parts of the threads should not be time sliced by the CPU. We can explicitly tell the CPU, these 4 lines, no time slicing. That's what we'll be doing. So very micro level control of the threads. Okay, and we need that. Otherwise, a race condition will happen. And God forbid, the patients using your system will get burns like just now. Or even worse, one of my colleagues from 20 years ago, while I was working, he left the company I was working with to work for Boeing. Boeing, very good job. He was based in US. About 5 years after that, remember the Boeing crashed because of a software fault, yeah? The software detected drop, so the software tried to correct the plane, but the plane ended up diving and everybody crashed. Now you would normally think, pilot's fault, right? The pilot is your concurrent program. The plane is of course full of threads, isn't it? Everything the plane does on autopilot, every element is controlled by an individual thread. Yeah. So these types of systems are what we call high reliable systems. It has to be reliable, isn't it? However, if you notice that Boeing was actually, and anytime a plane crashes nowadays, you notice they'll ground those planes. What are they doing? They're not really checking the mechanicals. They're checking the source code. Yeah. So we have to be aware of the potential of where your code is going to serve. And we have to learn the right techniques to ensure the known problems, which we have learned over the last 50 years, can never occur. Yeah. All right. So yeah, we'll be using threads, obviously. Each thread will have a runtime stack. These are things you should know about the thread. So each thread is controlled in terms of how it runs by the OS. Yeah. This is what we'll be learning to do: synchronous communication. Okay. There are also asynchronous methods, but we are not going to touch the asynchronous part just because we are limited in terms of time. Okay, I'll tell you what these are and why we are not doing it later. These are the terms the approaches we are going to use. We're going to be using locks. We're going to be able to make things mutually exclusive. So these terms I need you to use properly in your assignment and exam as we cover them, okay? Atomicity as well. Atomicity is, okay, what is an atom? Atom. Nobody learned science in high school. What is an atom? The smallest, isn't it? The smallest component of anything is an atom. So atomicity is where you have your program, but there are some things which should be treated as an atomic statement. What does that mean? You can't split an atom, right? You can, but then you'll have a nuclear blast. So you can't split an atom. It will be disastrous. These atomic statements you have to define in your program. Meaning, the one I mentioned just now, the CPU will know that this is an atomic statement because you said so. It will not time slice it as it's running it. Okay, we'll see the impact of that time slicing in the next few labs. More challenges here. It is difficult. It's more difficult than your normal sequential program. But if you learn the right techniques and you carefully coordinate the data, you can avoid the race conditions that we will be witnessing. Yeah. But this is still true. Yeah. The problems are hard to detect and hard to reproduce. You will see that later. It will happen sometimes, but sometimes it won't happen. This only happens, race condition, by the way, if you do not learn how to do these three things properly. And we will learn how to do these three things over the next few weeks. Okay. Every programming language offers similar support for concurrent programming. These are the terms we are going to be, you are going to be fully familiar with as the weeks go by. Yeah. And of course, one of the things we want to avoid is a deadlock. We know what that is, right? Deadlock. Your machine freezes. Nothing can happen, isn't it? Okay. How do we make sure everything runs well? We need to synchronize all these different processes carefully so that any thread you start, we want to make sure it finishes. We don't want to make sure, and we don't want any threads you start hanging and still roaming around the system, never ending, right? That's a bad thing, yeah? Then we have these types of things which happens in your machine and your laptop as well. Spinning, 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 right? That happens, isn't it? Why does that happen? There is a thread that has not completed its task. So the program is just waiting on something. But will it ever end? Sometimes not, right? Okay, we all witness this, isn't it? Especially if the connection is bad. The thread is waiting for some response or something, but never gets it. So you just see the spinning progress icon there, right? So a distributed program is also called grid computing. Use these two terms interchangeably. Yeah? Okay, so in summary, you should be able to describe, perhaps in a paragraph, this picture in a nice paragraph words. Yeah. Okay. Use coffee machine if you like, but I'm sure you can express it in your own words. You understand the concept, right? Okay. So this is what we'll be doing in the lab. I don't think we can actually start doing anything right now. So I think, but those of you who already did this yesterday, tomorrow and Thursday lab, this is what we'll be doing. Yeah. There's two ways to create a thread. One is by extending the thread object. So bear this in mind. And the other way is to implement the runnable interface. Okay. So here, a thread object, if you extend a thread, can you extend another class? Can I class my thread, extends person class, for example? Can I extend from two different parents? Yes or no? You all know Java, right? Yes or no? I only get a response if I run Slido, is it? Can Java support multiple inheritance? That's a technical question. Huh? So no, yeah. The answer is actually no. Extends thread means that's it. My thread only can inherit from its one parent, extends thread. I cannot extend from another class. So Java does not support multiple inheritance, which is why we have two ways of creating a thread. Yeah. So those who did the thread yesterday, now you understand why we have two ways of doing it. Yeah. So here, this is how what we'll be doing tomorrow as well. I'll create a new thread object so that this thread is a full thread object. This is where you extend from thread. Yeah. Then if I need my class to be a thread and yet extend from another class. So maybe I'm a lecturer, right? I extend from person because I'm also a person, but I need to run as a thread. So I cannot use lecturer extends thread because I need to extend person, right? So what I'll do is class lecturer implements runnable. So I'll behave like a thread. Runnable is an interface which behaves like a thread, but it's not a full thread object. So just bear this in mind first. Tomorrow when we do the two different types, we will understand why there's two types. That's what we're trying to say here, yeah? So here, these are the things we can do with a thread. We can start it, which we will do tomorrow. Some of you did yesterday. Once you start a thread, it will automatically call this run method. So these things are best to just do rather than for me to actually tell you, yeah? But just take note that a thread will start, it will run, and once it finishes running, it will be terminated, yeah? So that's what we are going to be doing this week. All right, we can do many things. We'll cover most of these within the next few weeks. Here, just take note of this method here. Once you run a thread, you can put it to sleep. Sleep means you pause the thread. You ask it to sleep for a certain amount of time. We'll also be doing that many times, yeah? So here's the main difference between the two. Also, you might need to answer this in the exam. When would you choose one way over the other? When would I choose extends? When would I choose implement runnable? Yeah. So it's your call as the programmer. That's why it says a matter of taste. Yeah. So here, basically, yeah, you choose implement runnable if you need to extend from another class. But this one requires a little bit more work. So next week, we'll talk about that extra work that we need to do. Yeah. But if we don't need to extend from other classes, extend thread is the easiest way to do. Because whatever your class is a full thread object. Immediately, you can do everything you need to do with the thread. Yeah. The only downside is your class can no longer extend any other class. So implement runnable behaves like a thread, but I can still extend from other classes. Whereas extending thread, yes, I am a full thread. I can only do things that a thread does. I cannot extend from any other parent class. Okay? So that's the main criteria here. So in your assignment, if your class doesn't have to extend from any other class, make life easier. Which one will you choose? Implement runnable or extend thread? Extend thread, yeah? Okay. All right. So here, I think we'll just take note of some of the life cycle here before we adjourn. So when you create a first a thread, it becomes created or it becomes a new thread object, a new thread, yeah? Then you can start that thread, the thread becomes alive. And once the thread becomes alive, it will automatically look for a run method in the thread. So all thread code must have a run method. Otherwise, that thread doesn't know what it's supposed to do. Okay. Then you can, once it finishes the run method, it will be terminated. Yeah. So this alive box here, right? We're going to go into that box. While it's alive, it can be running. It can be asked to stop running for a while, where you can ask it to sleep, becomes non-runnable. Once that sleep time has lapsed, it becomes runnable again. Yeah. So while it's running, doesn't mean that it won't stop. It will stop for reasons you will determine. Okay. And then, of course, everybody remembers encapsulation. We have to make sure of these things. These are things you already know, right? Okay. So the threads have to keep track of the encapsulation properly. Otherwise, your data is going to be messed up. Remember, yeah, a lot of things are happening when you run threads. So the access modifiers have to be established properly. All right, we will look at this, I think, next week in the lab. Sorry, next week we'll come back to this class and relook at this thread example, yeah? Okay, I think we will stop here because we don't have time to do any coding today. Yeah, next week onwards. So I ask you to bring your laptops already. Next week we'll definitely do some coding in the class. Yep. Okay. Any questions? No, everybody's ready for lunch. Okay. Get your attendance in, please.